topic is microlocal sheaf categories and the J-homomorphism. One goal is to show some results on microlocal sheaf categories over general coefficient ring, like ring spectra, and then it's naturally connected to stable homotopy theory. And another goal is to show some applications. So here is the outline. So first, I will give some very basic background on microlocal sheaves in case you haven't seen this before. And then secondly, I will focus on microlocal sheaf categories on smooth Lagrangian. So where we will see a local system of categories on Lagrangian, and then which admits a classifying map to a classifying space. And then thirdly, I will state the main theorem and show some applications. And lastly, if time permits, I will also say something about the idea of the proof for the main theorem. So first, some background. So first, some basic notion for sheaves. So if you have a topological space X and a fixed coefficient ring K, so we assume it's commutative. And if you're familiar with stable homotopy theory, you can also think this K is a ring spectrum. And then we can consider the large DG category of sheaves on X with values in K modules, and this will be denoted by sheaf XK. So in concrete terms, so what is a sheaf? So a sheaf is an assignment for each open set in X, a K module. So here, because we are considered like DG categories, so if K is an ordinary ring, it's like a chain complex of K modules. And then you should assign like restriction maps for the sections over each open set. And then when you have compatibility with for restriction maps, then you naturally have a pre-sheaf. And then the sheaf condition is some extra condition on like a Melville-Torres condition. So that means a big open set, you can get the sections from gluing from open cover, from sections on open cover. Okay, so just a recap of sheaf definition of sheaves. And then for locally compact Hausdorff spaces, the sheaf theory has a very rich structure. So you have the Grothendieck 6 functors. So this, you have the pullback of sheaves, and then it's right adjoint, which is push forward. And then you have the dual version. We have the upper shriek pullback, and then you have the left adjoint, which is lower shriek push forward, or sometimes called push forward with proper support. And then you have the tensor and the internal hum. So yeah, so we will pay our attention to locally compact Hausdorff spaces unless otherwise specified. Okay, so then for microlocal sheaves, this is developed by Kashiwara Schapira in the 90s. So the key notion is the single support of a sheaf F inside this category. So here we should, assuming X is a manifold, if X is singular, what you do is you embed into some manifold. And then this gives us a connection to symplectic topology, because this single support lives inside the cotangent bundle, and is, from definition, it's a closed conic subset inside the cotangent bundle. Here, I choose the convention that I delete the zero section. So I only consider the complement of the zero section. So roughly speaking, so this set collects all the covectors where non-propagation of sections of F occurs. So that means you see some jump of sections when you move in the co-directions inside this closed set. So just to show some very simple example and give you some sense what this single support look like and how it's defined. So in this picture, I'm drawing the phase space of T star R. So this is Q, this is P. So this P index like some multiple of dq. And then, so here I draw the single support of two very standard kind of sheaves. So the green one is the push forward of constant open interval AB. And then the red one is shrink push forward of constant CD. So just recall that, so for just a sheaf, the support is on this closed interval for each of them. And then the difference is that difference between these two kind of push forward is that this star thing, when you take an open set near this A, near this border A, what you see is the section space is isomorphic to K, and similar to B, similar for B. However, for shrink push forward, when you take an open set containing just this border D, then you see zero section space. Okay, so now I will show an example how you detect the single support of these two sheaves. So I start from half, like in infinity interval. So it's from negative infinity to this point. And then I just compare sections compare sections of this interval, and after I cross a border directed by this covector. So I change the border of my open set, directed by this covector. So for example, here, starting point at the starting point, the section is 0 because it's away from the support. But when I cross C, I see some interesting thing happen. So because this intersect the support of my red sheaf. However, as I said, this section is still 0 here. So there's no change of section of my sheaf. So that means there's no single support in this positive direction, positive multiple of dq. On the other hand, if you cross this A border for this green sheaf, then you see jump in the section space. So the jump is by K. So that means you see a single support in this positive way. Okay. So you can complete this exercise. So you can move forward here. And also you can test whether there's negative ray in your single support by moving like a border of this half, like kind of interval. So any questions? Okay, great. So an important theorem of Kashiwara Schapira is that the sheaf, for any sheaf F, the single support is always co-isotropic. So closely related to symplectic geometry. So just to recap some history of symplectic geometry. So the starting point is the study of cotangent bundles from classical and quantum mechanics. And the interesting objects are those co-isotropic subvarieties where the position and the momentum of a particle lives. So this is because by Heisenberg uncertainty principle, you cannot have anything smaller than a Lagrangian where you can detect both position and momentum. Okay. So, and the single support appears in many different branches, including PDE and D modules. So this is more like an algebraic version, and with different definitions, but intimate relations. So the main problem there, so the key topics in those areas is to quantize a given co-isotropic subvariety. So in more explicit terms, you want to find sheaves, differential operators, or D modules with single support in a certain given co-isotropic subvariety. So upshot for this approach is that this kind of quantization give us interesting invariants of these co-isotropic subvarieties. So definitely have applications in symplectic geometry. So for example, to tell that two Lagrangians are not Hamiltonian isotopic, then you can try to show that their associated quantizations are different. That's one typical approach. So here, just to advertise some applications of microlocal sheaf theory in the study of symplectic topology. So over here, such applications are firstly due to Netherland-Zaslow, so who showed that who built an equivalence between a Foucault category on a cotangent bundle with sheaves, constructible sheaves on the base manifold. And the Tamarkin also used like sheaf quantizations to give conditions on a non-displaceability of two Lagrangians. And his approach is roughly what we will take in this talk. And just list a few subsequent applications, which of course I omitted many important, interesting results here. So, so for homological mirror symmetry, first we have this joint work, Feng, Liu, Truman, Zaslow. So they prove homological mirror symmetry for toric varieties, and Nedler proved homological mirror symmetry for pair of pants, where so which is non-toric case. And then for sheaf quantizations, so the starting point is Tamarkin's work, and then Guillermou, Kashiwara Schapira prove quantizations for Hamiltonian isotopies for Hamiltonian flows, and then also Guillermou applied sheaf quantization to study Lagrangians in cotangent bundles. And then contact non-squeezing, so Chu proved this contact non-squeezing conjecture using Tamarkin's approach, based on Tamarkin's approach. And then also there's some work relating sheaves for Lagrangian knots and Lagrangian contact homology. Just list a few.
Xin?
Yes.
You have a question from Oleg Lazarev. Oleg, you can unmute yourself and ask the question.
Yeah, okay, great.
Hi, Xin.
Hi,
I was wondering if you can distinguish coisotropics that are not Lagrangian this way, whether there's been any results in that direction.
Yeah, I don't know any results in that direction. Because, I mean, for sheaves with single supporting coisotropic but not a Lagrangian case, I guess it's much more complicated than Lagrangians. So yeah, but so I think Tamarkin has some work on like studying like balls, symplectic balls, but I'm not sure about his results. So sorry. That's certainly a very good question. So of course, if you're coisotropic, then it's the whole symplectic variety. Then you just study like all possible kind of sheaves. So yeah, maybe let me just say I don't know.
Okay, thanks.
Okay, so so maybe just a comment for coefficient ring. So Kashiwara Schapira, the original theory is based on ordinary ring. And then for ring spectrum, one can generalize their theory to some extent. So for example, Schapira had some steps in this direction, and also previous joint work with Truman, we tried to do something in this direction. I guess this is not completely done, but I mean, as our focus is just on sheaves with single support in Lagrangian, which is like the easiest case, the theory can be generalized without much difficulty. And so similar to like the developing theory of lower homotopy types, by Cohen, Jones, Siegel, and Abouzaid Kragh, and I guess also some subsequent works. So the hope is that if you introduce general coefficients and bring new techniques from stable homotopy theory, you might be able to say something more about symplectic topology. To have some more results about like Lagrangian submanifolds in symplectic manifold. So, so the next topic is focus on microlocal sheaf categories on a smooth Lagrangian. So then the goal is to show this naturally defines a local system, locally constant sheaf of categories on a smooth Lagrangian. So, so we'll focus on the following settings. So L will be an exact smooth Lagrangian. So smooth is important. And then exact means, so you restrict your canonical primitive to L is an exact one form. And then we will fix a primitive. So then, so what Tamarkin did, I mean, his approach is to conify a non-conic Lagrangian into a larger space. So then you can study sheaf with single support in it, because we know single support are conical Lagrangians. So in this way, you transform a non-conic one into a conic one. So you can use sheaf theory to study it. Okay, so the conic lifting is quite explicit. So here, what I mean by this negative cotangent bundle is that it's like an open subset of this cotangent bundle where this dt coefficient should be negative, so it's negative tau. And then to get the conical Lagrangian lifting, so first when tau equals 1, what you get is like a contact hypersurface, which is the same as the one jet space for X. And then in that contact hypersurface, you can define this Lagrangian from L. So it's just you collect QP from L, and then you just take T equals this function of QP, and tau equals 1. Okay. So then the conic one is just a standard procedure where you just take the cone of it. So homogenize this thing. So from contact hypersurface to this this part of the cotangent bundle. Okay. So the best way to see this conical Lagrangian, which is equivalently a Lagrangian in that contact hypersurface or jet one space, is to look at its front projection. So X times RT. So this is a picture where you have the Lagrangian L, the original one in the cotangent bundle of R. And then when you do this lifting, then its front projection is of this figure. So you see an interesting cusp here because you have some tangency of your Lagrangian with the cotangent direction. Oh, yeah. So then when you try to read off the Lagrangian or the conical Lagrangian, so you just draw the conormal vectors to this singular hypersurface. Then you have all the data of this L. So then now we can assign a sheaf of categories on L. So for each open set omega in L, we will assign the microlocal sheaf category with single support in cone of omega. This is part of conical Lagrangian, not closed. So it will be denoted by mu sheaf sub L sub omega. So the definition is a little bit involved. So there's a more general construction, so not limited to Lagrangians, so by Kashiwara Schapira. So, however, in this, for this Lagrangian, for our situation, there's a more like an explicit definition of this mu sheaf omega. So we'll do the following thing. So if L is in a general position, that is, we assume that the projection of L to X to the base is everywhere finite to 1. And then we'll take our omega to be a small ball. Then we can use, then in this front projection of the conic lifting, we can use a small ball, a small box of this form. So you have a like an open set in the base of X and times an interval of the RT direction. And you can use a box to cut out like a closed image for the front projection. And then you forget about other possibly overlapping branches. So then once you have this picture, you can define mu sheaf omega to be sheaves with single support in this conic Lagrangian. And then you quotient out by the local system on this box. So in other words, you do like the right orthogonal complement of local system. And in this picture, it's just putting 0 in the far below, far bottom region. So then maybe I'll just state a proposition which is the basis for showing that this defines a sheaf local system of categories. So, so for any small ball omega in L, we have this mu sheaf omega non-canonically equivalent to K modules. So this is a picture. So how you possibly assign a K module to this mu sheaf omega in this two pictures. So here you have like a Schrick push forward of a constant sheaf here, and here you have like a cusp. So you do a star push forward on the upper branch and doing a Schrick push forward on the lower branch. So let me just give the sketch the proof for this proposition, which is related to the idea for proving the main theorem that I will state. So the proof goes as follows. So for such a omega, you can always find a local smooth hypersurface in the product B cross B. So B was our box. And then, so this has the feature that it's a negative conormal bundle gives a local conic symplectomorphism of this open half cotangent bundle. Equivalently, this is a symplectomorphism of T star X, also local. And then it's also special in the sense that it's sends omega to a local graph Lagrangian omega prime over the base. So that means, so your omega originally might have some tangency with the cotangent fiber, but after this transformation, you should see a Lagrangian, which is in the generic position that is submersive to the base X. So once you have such a hypersurface H, you can build a correspondence like this, and then if you do the pull back, push forward operation, then this will transform the mu microlocal sheaf with single support in omega to a microlocal sheaf with single support in this omega prime. But this omega prime is very nice. It's some like a standard picture like this. So you have a natural way to identify it with mod K. So yeah, so that's how you prove that this mu sheaf omega is can be identified with mod K. So any questions? Okay, great. So so maybe we'll just give a name for this correspondence. So this H, we call it a generic contact transformation in the sense of Kashiwara Schapira. So that they call this contact transformation. So yeah, so really this H is like generic, and then and it's related to like stratified Morse theory, and we'll call it a Morse transformation for omega. So so then to say that it defines a locally constant sheaf of categories with fiber equivalent to mod K, we just look at the restriction maps, restriction functors. So if you have an inclusion of small balls, then the same correspondence H works for omega prime, the smaller one. So when you build this equivalence, where you transform your omega into a standard picture, the same holds for this omega prime. So on the right-hand side, this restriction is the obvious restriction from a bigger hypersurface to a smaller like smooth hypersurface. So you have this equivalence, and then because this is a commutative diagram, this shows you that this restriction functor is an equivalence as well. So in conclusion, this collection of categories, assignments of categories, gives a locally constant sheaf of categories on L with fiber equivalent to mod K. So we'll denote it by mu sheaf sub L. Okay, so okay, so now we are going to state the main theorem and see some applications. So a natural problem is the following. So for given a smooth exact Lagrangian L and a commutative ring spectrum K, so as we have proceeded, we have constructed a sheaf, a locally constant sheaf of categories on it with fiber equivalent to mod K. So then such a sheaf behaves like a fiber bundle. So so it has it's determined by a classifying map. So L to the classifying space for like the automorphism, K-linear automorphism of mod K. So this is equivalent to the delooping of like the so-called Picard group of K. So the maybe just a few words about this Picard group of K. So this is infinite, so-called infinity group. So first, what are the object? The object are invertible K modules, and then the morphisms are K-linear isomorphisms between them. So everything is so it's like a groupoid, and then so infinity groupoid because you have like a space of morphisms rather than just a set, and then it also has this monoid structure, so you can like tensor two K modules or K invertible K modules to get another invertible K modules, and then because everything is invertible, so it's also a group. So then you can deloop it, and if K is very commutative, it's like commutative, then you can deloop actually infinite many times. So then the natural question is, what is this map? Is there a symplectic characterization of it? So our main theorem is, let's try to answer this question. So, so under the same setting as before, we prove that this microlocal sheaf, this sheaf of microlocal categories is classified by this composition where the first one is the Gauss map to the Lagrangian Grassmannian, and then the second map is to this classifying space, where you see some like the famous J-homomorphism is the delooping of the J-homomorphism. We'll see a quick recap of this J. And then the last one is the tautological one. So because this sphere spectrum is like the initial object in all ring spectrum. So just recall the J-homomorphism very briefly. So you have this union of BON, so which are like Grassmannians of dimension n subspaces. And then the right-hand side is the Picard group of S. So as I said, it's like S lines, which are like invertible S modules. So then the assignment is to each vector space here to the suspension spectrum of the one-point compactification of V. So both sides have like this commutative monoid structure, and this J respects these structures, and usually also one do like a group completion of this BON. Then you see one of these Bott spaces. So this is one after the group completed, becomes like a Z cross BO. And then this map is an infinite loop space map. Just related to the ordinary setting. So if K is Z, then the classifying map is some familiar stuff, which gives the obstruction for it to be trivial is the usual brane obstruction in the Fukaya category given by the Maslov class, and obstruction to a relative pin structure. And this also has been obtained by Guillermou. And then maybe just one word about choice of background class in Fukaya category. So here, actually, secretly, we have chosen some natural choice of background class, which is a lifting of this composition of maps, which we'll see later in a more general setting. So this is like factor through BU. So you have this classifying space of your a classifying map for your symplectic frame bundle. So then this map is like from the theorem, it's like the double delooping of the J-homomorphism. And then choosing a background class is choosing a lifting. So then the standard one is induced from the cotangent fiber. So you do this section to the stable Lagrangian Grassmannian, and then you map to this it's like universal space, contractible universal space. And then you can, of course, you can like twist this map by some map from X, T star X to BPic. And then the resulting classifying map, it classifies twisted sheaf of microlocal categories, which are given by microlocalizations of twisted sheaves of K modules on X cross R. So the twisting class is given by this map. So this is something more general. And then, so I want to, before giving some proof, probably I don't have time, I guess. So I'll first show some applications. So the first application is that if you have a compact, smooth, and exact Lagrangian inside T star X, so embedded, then this mu sheaf is actually trivializable. So in particular, by the main theorem, the composition of this map is homotopically trivial. So the last part, so this has been obtained by Abouzaid Kragh using floral homotopy types. So here we try to give sheaf theoretic proof. So just remark that if Arnold's nearby conjecture were true, then this gamma would be trivial. Then it implies this, but to show gamma is trivial seems much harder than this. But we have seen some progress in this direction from some previous talk, I guess by Daniel. Okay, so so let me try to sketch a proof for this application. So so step one is the sheaf quantization result of Guillermou, generalized by previous joint work with Truman over ring spectra. So the sheaf quantization, it's a fully faithful functor. So this is the content of the theorem. So so you have this conic Lagrangian lift in the front projection. And then the sheaf quantization is like you have some global microlocal sheaf, which is a global section of this sheaf of categories. And then it gives you a local system on X, on the manifold X. So roughly speaking, what this goes is that, so first you have an equivalence of categories between this microlocal sheaves with sheaf with, I mean, the category of sheaves on this total space with singular support in this Lagrangian. And then you also demand it to be like 0 far below. And then this is an equivalence. And then once you get the equivalence, so you assign each microlocal sheaf or actual sheaf. And then what you do is that you just restrict to a very high level surface, which is the same as X. You can do like pullback or maybe a shrink pullback. That's what I take. And then this is uses fact that this Lagrangian is embedded, exact, and also compact, because once it's compact, you don't see it in the far top side. Okay. And then, so one can also get a twisted version of this, which is also, I mean, used in Guillermou's paper, try to prove that this result. So this pi L from L to X is a homotopy equivalence. So then let's denote this X one homotopy inverse as per se L. Then we can get a twisted version of this quantization functor, which is still fully faithful. So so instead of microlocal sheaves, I twist by its dual local system. So then this is equivalent to a trivial local system of categories. So the global section is log LS. And then if you run the same argument, you get a twisted local system on X. So the twisting is just a pullback of this twisted sheaf of categories. So then the goal is to show that this twisting is trivial. So then of course this I mean this mu sheaf LS will be trivial as well. But this is equivalent to show that when you quantize here I choose my monoidal unit to be omega L because I do the like a shrink tensor. So anyway, so you just contact the monoidal unit of your local system, then it should have like co-stalk or stalk if you prefer, isomorphic to an invertible S module after you choose some trivialization or local trivialization of this local system of categories. And more intrinsically, that means, so if you restrict to like contractible open thing, open ball, like a contractible ball, or maybe a ball is contractible, yeah, contractible open thing, then it should give a section which is compact. I mean, it's a compact object, and its isomorphism should be isomorphic to S. So the compactness is almost obvious, because if you try to quantize this to be a sheaf, then the stalk or co-stalk here is from iterated, finite steps of extensions of invertible S modules. So it's a perfect S module, so compactness no problem. So the question is, what's the isomorphism? So any questions? Okay. Okay, so this part is like a little bit it's technical. It's just it's not that necessary. It's just I'm just used to think in this way. So I changed my functor to the dual version. So originally, I mean, people usually take star, upper star, lower shriek. Here I take upper shriek, lower star. Then the tensor will be shriek tensor, and my monoidal unit for local system will be the dualizing sheaf. And here I take in this way because I want to extend my functors, adjoint functors between local systems. So I have upper shriek, and then it's left adjoint, which is the same as the usual F lower shriek if F is locally trivial vibration. So I want to extend this pair of adjoint functors to the infinity category of topological spaces. So this is because, I mean, to this step, we're only talking about local systems. So then we can go out of the space, go out of the category of like manifolds to the like infinity category of topological spaces. And then the functor, I mean, naturally extend. So then another important thing is that this functor has more structure, so it respects the action of local system on X with like this shriek tensor on both sides. So so the action of local system X is essentially just given by tensor with its pullback. So for if you get the left-hand side, so M is inside here, which is some kind of twisted microlocal sheaf, then you can tensor with the pullback of any local system on X. Then by simple observation, so this is the resulting quantization is the same as the quantization of M tensor with L. So that's roughly, so that's roughly because, so if you, so this tensor corresponding to your sheaf with microlocal support in here, whose microlocalization gives M, and then you tensor with the pullback. So this corresponds to that, but then when you restrict to a level set, it's correspond to this local system tensor with L. And now we can do some adjunction and then compute endomorphism of, so yeah. So maybe let me go from the beginning. So what do we want to do? So first we use the homotopy Cartesian diagram. So we have X, and then we have this universal, universal space, contractible space. Fiber, homotopy fiber are the loop space of X. And then because L to X is a homotopy equivalence, So the pullback of this vibration is just a path on L. Now we can apply to the case where my M is the dualizing sheaf on L. And then I try to twist my M by this local system from like upper shriek, lower shriek. But this is the same as just a lower shriek, the monoidal unit here, whose fiber, or maybe you say co-stalk, are computing the homology of my fibers. And then you just realize that when you tensor, it's the same as just doing upper shriek, lower shriek, and then this is a lot of words. So then you can use some adjunctions for categories of twisted local systems, and the fact that when you pull back your twisted local system on this contractible space, everything trivializes. So then if you try, so then using this is fully faithful, when you compute the harm between this M tensor with this pullback with M itself, this is isomorphic to the harm between this thing with QL twist M. Then you get, and then using adjunction, you get this isomorphism. So this isomorphism tells me that when I pull back my twisted local system, which becomes a local system there, is isomorphic to just pull back my omega, which is just the omega here. And then this is isomorphic to S. So then this completes the proof. So any question? Okay. So this proves application 1. So application 2, it's try to define a microlocal category on a Lagrangian skeleton. So not necessarily inside a cotangent bundle. So the general setting is that you have some Liouville manifold M, dimension 2n, and you have a Lagrangian skeleton there. And then you can consider this stable symplectic frame bundle on M, which can be reduced to a U bundle when you choose an almost complex structure. And then the idea is that, so you can think of local sections for this frame bundle on a small ball, maybe up to homotopy. So maybe you choose a better replacement for this space. So this parameterizes like stable R equivariant contact embeddings from this ball into the standard symplectic space, or maybe the contact version. So then for their image here, so you get a family of, so for each open set in your lambda, you get a family of Lagrangians, and then you get a family of microlocal sheaf categories. So then the upshot is that this sheaf of microlocal categories, so this defines a sheaf of microlocal categories. You can say on F, so this frame bundle restricted to lambda. And this has some nice structure that with respect to the U action on the fibers, it's twisted equivariant with respect to a character, which gives you like a local system on U with fiber mod S. Then the idea is to like do some twisted equivariant descent, and you ask when this can be, this sheaf of categories on this larger space can be descent to a sheaf of categories on lambda. And then the theorem, which is in preparation is that the obstruction to the descent of this to a sheaf of categories is classified by this map. So you have this classifying map of the frame bundle, and then the second bundle comes from like this U. So this character is from like composition of first U to U mod O, and then composed with the Bj. So it's almost immediately following from our main theorem, but of course one still has to write down some details. And then suppose this is homotopically trivial. So that means you can choose a section, choose a lifting of this map. Then the sheaf of categories on this frame bundle restricted to lambda descends to a sheaf of categories on lambda. And then again, so you can, so there's no canonical, in general, there's no canonical choice of this lifting. So once you have a lifting, as we see, you can define kind of a Fukaya category. And then as in the cotangent, similar to the cotangent case, so for smooth Lagrangian, you can define like a relative microlocal sheaf category on it. And then its classifying map will be a comparison of these two maps. So first map you have in bed, and then composed with your choice of lifting, and the other is this L naturally gives a section of this Lagrange Grassmannian over itself, and then you compose with the natural map that is from the from the J-homomorphism, as we have seen. And then so just to collect some related results about constructing like spectral Fukaya categories. So Shende has a construction for such kind of Fukaya category on a Liouville or Weinstein manifold. So using H principle, so closely related to ours. However, his complete version over ring spectral will rely on our main theorem. And then from attending several talks recently, so I've learned that there are Abouzaid and collaborators, and Tanaka and Large have works on constructing spectral Fukaya categories, and maybe some are in progress. So if I understand things correctly, so these should all be equivalent. On the other hand, so Tamarkin has a version for compact symplectic manifold, which from my point of view, it's much more advanced. Okay, so yeah, surprisingly, I still have 5 minutes. So maybe I'll just say something about the main idea for the proof. So just recall this as our main theorem that the classifying map factors in this way. And the idea of a proof, so for simplicity, let's just assume X is Rn. And then the first key observation is a connection between Morse transformations. So as we have seen in the previous slide, so these are the like generic contact transformations. So this give paths in U mod O based at the zero section. So here I will illustrate by some picture. So maybe more technically speaking, so you always model out some obvious equivalences by composing your symplectic morphism further by some symplectic morphism from like diffuse morphism on the base. So you always quotient by such things, and then this Morse transformations, I mean, have roughly gives all the paths in U mod O, up to a group completion. So here's some picture illustrating what's going on. So I draw just some linear Lagrangians. And then most transformation does the following. So you first do a Fourier transform. So you rotate everything counterclockwise by 90 degrees. So this is considered as one part of your path. And then the goal is to reach the zero section. However, as we all know, there's open stratum in U mod O consisting of all Lagrangians that are submersive to the base. So this open stratum is contractible. So in fact, we don't need to really reach the zero section. We just need to reach to this very fat base point, the open stratum. So that's the goal. So for example, here, 3 of my Lagrangians already reach this open stratum. So they already complete a path from the original one to the base point. However, my red one doesn't reach that stratum. So what I can do is just further compose with Hamiltonian time one map of a quadratic Hamiltonian function, really completely depending on the momentum variable. So my quadratic Hamiltonian function will be like Q of P, and then I do a time one map. Then this is enough to displace my, to separate my Lagrangian from this cotangent direction. So for example, in this, if I compose this, I complete one path. And then you can further do another one, which will like, so reach another path, but the difference is like Maslov index 1. Okay. So based so up to some group completion. So based loops in U mod O can be obtained from time one maps of this non-negative quadratic Hamiltonian. So if you start from like a slant Lagrangian, where you see like it's like a D of like a positive like a quadratic graph of D of a completely positive quadratic function, then you could just do this Hamiltonian map and sorry, the wrong one. Oh, yeah. So then you have some loops. So then you have different loops attached to different choices of Hamiltonian functions, like non-negative ones. Then this is like a more detailed formula for this. And then for non-negative quadratic Hamiltonian functions, so essentially what you need to know is just it's like a support. So it's like a vector, a dimension n, a vector space with some like eigenvalues attached to it. So then up to homotopy, this is equivalent to just disjoint union of BONs. So that's the connection. And that's connection. That's a one way how Hamiltonian dynamics or maybe Hamiltonian functions can give loops in U mod O. So then through this approach. Okay. So then maybe So I'm okay. So now once we have established such connection, then if you pull back the universal omega U mod O principal bundle on this classifying space, then you get like omega U mod O principal bundle on L, and then you can think of so then this fiber are like paths from your tangent space to the base point, to the zero section. And then, however, so by our link, you can consider this as parameterizing Morse transformations. So roughly, And then this gives a family of trivializations. So using our correspondence description, so that you get a family of such equivalences. In particular, for each object in here, you get like a local system on the fiber. And then the key proposition is that under this observation, so the local system that you get have some twisted equivariant structure. So not like arbitrary local system. So these are so you have a canonical, maybe natural identification. So by some family of correspondences that gives the equivalence between mu sheaf omega with local system with a twisted equivariant structure. So and you can make this compatible with restrictions. So at the end, once you have this identification by some like tautology, the theorem follows. So then this sheaf of categories is classified by something like first map to U mod O and then the delooping of this J. Okay, of course, yeah, you have to write down many of the details because there are a lot of structures here. So you need some machinery to give a precise and clean argument. So here we employ the definite two category of correspondences divided by Gates-Rosenblium and find some model that makes this work. Yeah, so then I'm done for the talk. So thank you very much for your attention.
Great, thank you. Let's give a round of applause for Xin.
Yeah, thank you. Okay.
So are there any questions for the speaker? Let's see, I had a question.
Oh, okay.
So after you first presented the statement of your theorem, I think 2 slides after that, you say that in the case when K is the integers, that this classifying map gives the brain abstractions and the definition of the Fukaya categories. Could you say a word about how to see that?
Is it this one?
Before the first time that you give the theorem.
Oh, okay. So yeah, so if you put K equals Z, so then this peak Z is, I would say roughly, it's like a Z cross B Z mod 2. So I'm a little bit hesitant about like splitting a structure as like an infinite loop space, but yeah, let's just say like it's Z cross B Z mod 2. And then, so then this composition is like L to BZ times B squared Z mod 2. So then, yeah, so then if you go to the J-homomorphism, so then what is this, or maybe BJ, so it's like, I mean, essentially you want to know what is this map from a U mod O to like BZ. So this is just, I mean, if you like do like loop, take loop everywhere, then you get like a Z cross BO to Z. So then it's just like project to this Z. And then that means, so, I mean, that means when you do this, what's that? This method of, so when you take a loop of U mod O, so we have this standard, as I said, this standard presentation of this loops in U mod O. So it's like you just rotate by 180 degrees. So that gives you a loop. So and that one just send to the generator 1 in Z. So then that means, I mean, that's just a loop on L to Z, so which is exactly the method of class. So yeah, so how many times like you rotate. So that's the method of class. And then for the second one to like B squared Z mod 2. So so actually that one, it factors through a sequence. So you have like U mod O, and then you do like B of O, because it's, I mean, you have this Lagrangian bundle over it, but it's also like a plane vector bundle. So you have like this classifying map to BO, and then you have this like a second Stiefel-Whitney class. So you have like this H2 like BO Z mod 2. So that's essentially this composition. So yeah, is there other way to say it?
I see. So
yeah, so yeah, and another nice way to see this is that this composition, I mean, this trivialization of this is equivalent to like lifting of your L to the like the universal principal bundle, this universal omega U mod O bundle. I mean, on the two up to the two skeleton of L. So it's like the obstruction to such a lifting up to like if you triangulate your L, it's like just to try to trivialize this up to your two skeleton. So that's the maybe a better way to see this.
Thanks for the explanation. Let's see.
Yeah, I guess.
So I have.
Yes. Who is?
So. So, for. Yeah.
Sorry. Sorry, I don't hear you.
Go ahead, Danny.
Sorry, one second. Can you hear me now?
Yes.
Okay, so in the cotangent bundle of a sphere, it was proved by Abouzaid, Kragh, Guillermou, and Kurt that you have in fact a map from the base to PIC-S, not BPic-S. Is there any way, do you think this can be seen from this viewpoint, or not really?
You say you have a sphere, then it's to peak.
Yeah, you can.
Then that's like a loop.
That's right. Yeah. I mean, they use generating functions. So the question is, could you see this just from sheaves, or is there some fundamental reason why you can't go one level up?
Sorry, I don't. So your L is a Lagrangian inside T star Sn. Is that what you're saying?
Yeah. Yeah, and then somehow you can go one level up and get a map to PIC-S, not to BPic-S.
So what I said. So what? Oh, you're saying the. Oh, I see. What? So yeah. So then this trivializes. So what I prove is that this trivializes. So then you can like choose a lifting, but is there a canonical? So is there trivialization from L to PIC-S?
It is not canonical. It is not canonical. I see. So this trivializes, and therefore you can prove you can pick a lifting. So you do get a map.
Yeah. But it's not canonical. Yeah.
Yeah, it shouldn't be canonical. Okay, I see. Thank you.
Okay. No problem.
See, are there any further questions for the speaker? So, Jin, if it's okay, we'll go into the discussion session.
Oh yeah, sure. Okay. Thank you
All
very
right.
much.
So thanks so much again. Let's give Jin a round of applause.
Thank you.